Happy birthday. Countdown.
Happy New Year.
Alright. So we're talking about limits. So up until this point, we have been doing pre-calculus, which is all the topics that you need to know in order to be able to do calculus. We haven't actually done any calculus this year. But this section is over basically the first topic that you learn in any calculus level course, which is limits. So this says, what is the function approaching as x approaches 2? So what are we wanting to look at?
The overall motion of the graph.
Yes? So what might be helpful to do?
Graph it.
Okay. What type of graph is that going to be? It's a parabola. Where is the vertex?
+2.
Plus 2 is going to be where my y-intercept is.
Oh.
So if I plug in 0, I get out 2. That's my intercept, right? However, that's not where my vertex is.
X.
Yes.
-1.
Nope. Does anyone remember our formula to find a vertex?
Oh.
No. No.
Almost.
A.
So what is our b value here?
-1.
So -1 gives us a positive 1.
1. Oh.
So then, if I plug that back in to get my y value, what do we get?
Good question.
1 3/4. A big number,
Which is also
like 7/8. Okay.
7/4, but yes. So 1.75 or 7/4. Okay?
It's not.
Monkey ball. Oh, this is exactly
Alright. So, do we know anything else about this graph now?
The vertex.
Okay, we know the vertex. What else do we know about parabolas?
They look like from you.
They look like a U. So what does that mean that they are? Symmetrical.
Oh, yeah.
So that means that if this is my vertex and I'm 1/2 to the left and I'm at 2, that means 1/2 to the right, I also have to be at 2.
And then you just go.
So the axis is
And then which direction is my parabola going to point?
Off.
How do I know that?
because that's the direction it's spreading out.
X squared is positive.
But also A is
In negative.
positive.
Yeah.
And where's that one?
So next, it's asking us, okay, so as my function is approaching, sorry, as my x value is approaching 2, so that's that second line, right? It asks what the function is approaching. What type of values are we looking at when it says what the function is approaching?
Y values. So, I don't know.
We want to know what y value our function is approaching. How do we figure that out?
Plug it in.
Plug in what?
2.
Big number.
Sec.
And what do we get?
4.
Did you also just like look at it to figure that out?
As long as you graphed it accurately, yeah.
Cool. That's
So that means we have a point right there. Are y'all alright with that?
Yes.
Okay. So we've looked at graphs, we've looked at function values, but now we're going to look at a different notation, which is our limit notation.
Oh.
So, this is the limit of f of x as x approaches a.
I should probably take a picture of this. Oh, you don't know it's online. right? You post the videos on the YouTube, or in Canvas rather. Ouais, j'ai mis YouTube.
Arbitrarily close. And to L.
Huh.
What do these words mean?
So,
Nice notation.
as x gets arbitrarily close to a, sorry, I skipped a letter there. Then f of x gets arbitrarily close to L, we say the limit as x goes to a of f of x equals L. Which, it's a funky notation, but it's not as hard of a concept as we think. Because basically that's what we did on those last examples. Okay? So, what x value were we getting closer and closer to? 2. So we would say we're looking at the limit as x goes to 2 of f of x, okay? And then what value did we say that our function is getting closer and closer to? 4. So that says the same thing as what we just wrote up here. It's just a nice, pretty notation, right? Just another way of writing it out to make it a little bit more concise, okay? Now, what does the word arbitrarily mean?
Like,
Almost.
it's like a general.
Like
Very
whatever you want
around
it to
there.
be. It means like
Oh,
you get to pick, or it doesn't have to be exact, or as close as we want, basically. Okay? So now, our first example here, okay, this is very similar to the one that we just saw. There is a point there. As x goes to a, whatever my y value of that point is what my limit equals. Make sense? That's like the last example. However, on like these next two, notice that there is a hole at a, but I said that we're getting arbitrarily close, yeah? That doesn't mean that we have to be at that a value. So if I have a hole in my graph, can I still get really, 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 really close on both sides?
Yes.
Yeah, so my limit still exists here, even though the function itself doesn't. Does that make sense?
Yes.
So basically, it's like if we didn't know what happened at A, but we kind of want to guess as to what would happen, that would be our guess. Like we would say, like following the same pattern, this is what it should be, even if it's not.
So
Yes.
if there's a hole in the graph, we don't have to change how we write it.
So like this one, my limit as x goes to a of f of x still equals L, but note that f of a does not equal L. So like there's a point here, right? So f of a would be whatever y value that is. In this case, we don't know what it is. And then on this last one, we would still write the limit as x goes to a of f of x equals L, but f of a is undefined in this case. And that's fine. Like I said, we do not have to have a point on our graph in order for the limit to exist. It just has to be getting arbitrarily close to some value L. Are we all okay with that?
Cool.
Not really.
What are we not okay with?
What is it on those?
What?
Why is there a hole in the
It's just the function itself. So sometimes when we have rational functions, they're going to have holes in them, or sometimes when we have stuff that have logs or radicals, they will also have restrictions on them. So it just depends on the function. also, if it's a piecewise defined function, then you can also have holes in the graph depending on how it's defined. Piecewise? Should remember piecewise.
No.
Oh, yeah.
That was like the first project we did this year.
That thing.
How is it?
I'm gonna throw a mark.
Because there's a hole in my graph. That's the only reason. Yeah. So the first one, the very first one is defined. The second one is also defined, it's just not continuous because I have a point right here. So it's defined because there's a point, it's just not continuous. This last one is not continuous and it's not defined because there's not a point. What?
Why is there a point there?
Because that's what the function is.
Okay. That makes more sense.
Like I said, it could be a piecewise defined function.
It looks a little better.
It's not a limit, promise. Alright, so this one says use the table to estimate numerically the limit. Okay? So, what did we do on our first example to find our y value? We just plugged it in, okay? So, what's our a value this time that we're approaching?
0.
What happens if we plug it in?
Great.
You get 0.
You get 0 on
We
the
get 0 over 0, which is undefined. It's not equal to anything.
It's not 1.
Because it's contradictory, right? Because anything divided by itself should be 1, but 0 divided by anything should be 0, and we're dividing by 0, which we're not allowed to do. So it's called an indeterminate form. You can't do anything with it.
Oh.
Okay?
Oh.
Indeterminate.
So it equals 1
Indeterminate.
and 0 and
Undefined, yeah. Which is why it's indeterminate. Okay? Which is why they tell us this time, instead of just plugging it in, we're going to look at a table.
Estimate.
I think it's just not a really
Now, what type of values do we want to plug in?
integers.
No.
Zero.
Can I? What do we say I get when I plug in zero?
No. Don't do 0.
0 is undefined, right?
Okay, so
However, we're approaching 0, right? So what type of numbers do we want to plug in?
Negative number.
And positive.
Okay, and positives. What's the thing? We're trying to get what?
Close to 0.
Close to 0. Arbitrarily close. Okay?
Decimal.
Now, is 2 close to 0?
No.
Depends on how you
Ish.
Kind of.
Is
Compared
1
to what?
closer to 0?
Yeah.
Okay.
0.1.
However, when we're talking about this, like 2 and 1 are not going to cut it. Like we're talking like
0.1.
0.01. Okay?
Okay.
So we're going to get real close.
Alright.
Real close and perfect.
You're not going
Amount
to
of
leave
zeros.
room for Jesus.
Like this infinite amount of zeros and a 1. Infinite amount of zeros and
Why are we
a 1
getting so
after.
close?
We gotta get close.
Why?
This is calculus.
Okay? Now, that's from the right side. Yeah, those are my positive values, but what can we also do?
Negative.
We can also have negative values.
Oh, you negatives and.
We love calculus. Oh, come on, Kakamala.
That's what I'm saying.
Okay.
I haven't been able to get back away from the polar graph.
Divided by.
Okay? So, you probably want to use a calculator.
Yes. Oh.
You either, I would probably use your table function, because then you just
Oh.
type in the function, and it allows you to evaluate it at any value.
Very smart.
Some movie.
Oh,
Oh, -1. Oh.
oh, sorry.
We get close to -1. No?
So, fill in your table, and then we're going to look at it all together.
Table.
Square root of
Table set.
square root of 1.1 plus 1 minus 1. And square root of 1 minus 1. Square root of 1.1. So the public is. Yeah, so it's 0.1 plus 1.
I don't know how to do this.
Oh, I forgot how you did it.
We have to.
Put table set up.
Oh,
Table.
We just have to move.
I'm gonna code this. You're gonna use
so f of x is
Oh.
equal to this stuff, it's not the limit. Is that
No.
Correct.
Table.
Yeah, just
Just
table.
plugging it into the living.
X equals 0.
Yeah, just plug it in. Why did she get I like this stuff where you just plug it in and then it gets you.
Table. Oh. Oh, point. Oh. And then I gotta put it in the box.
Table set.
Table. I changed my mind. How do I change my mind?
On what?
Or rather, insert.
Table setup.
Yeah, if you
Yeah.
go to second window,
Yeah, I did that.
then you can change the little where it has like the triangle X. That's gonna change the increments that it goes by. You can also change the starting value and just put in the starting value that you want it to plug in.
Right.
No.
What am I doing?
Then you click second graph and it gives you the table.
Oh.
Second graph.
Wait, yeah.
Yeah, that's what happened. Well, let me check it.
I get my table, but I don't have it.
Wait, let me work.
I don't have a ball. Like I don't have, you know?
How do you make a fraction?
You're
How do you make
I
it?
changed the
One
one.
over
I
one.
don't know what you did.
No, like
I'm using
this.
mine.
I'll make it look like that. Yeah,
Of course you did, bro.
Why is it such an advanced calculator?
What are you trying to do? A fraction is alpha y equals
Like this.
alpha y.
Oh, my calculator's still.
Like this.
Yeah, like you say it look like that. Oh, did we just type in the?
No, like this one.
That is so clever.
I didn't know that.
Wait, what
Now
did
you
you
do.
do? You just type in the equation.
Mom.
And we're just putting the numbers into the equation. Okay, we're just putting the 0.1 and then we're plugging it in for x.
Graph.
And you guys are just gonna take hours doing this.
She said 0.
I got
How do you make it?
I got negative.
After?
No, because my calculator is already pre-made. It's in
-1. All I get is errors.
No.
Wait, how do you make it?
You said
You get negative 0.09 pi on.
I got -1. I'm so confused.
Alright, what did we get? So if you can't figure out how to do it, then just plug it in straight up.
I got -1 and $20.
Wait, that's a lot.
Oh, that's fine.
Dude,
So funny.
so for you.
It's really close to this.
Alpha y
Does
equals.
it work? Yes.
Boom.
Literally change the numbers.
Why equals that?
What?
You plug in -1, negative, no, you plug in 0. No.
No, I'm plugging in 0.1.
Okay, so negative.
I didn't graph it, I just did it through my
You just plug
calculator.
it in.
Go here and put x.
What?
Yeah, you can also use your graph and then just type in, and you click trace and then type in the number that you want.
Hello, that's not
Oh, that's.
I did this.
Wait, do the graph and then. So do the y thing.
Schwarzschild.
I like green.
My graph doesn't have enough slots in it.
How do I read numbers?
It doesn't have enough. It doesn't have enough slots.
Okay, just plug it. The X.
You put the x
I
on?
just calculated that. It's weird, but the X.
It doesn't have enough slots.
Then you can space.
Oh, bruh, it's because it didn't have any parentheses.
L plus boson plus ratio.
I don't know.
Right now I
Here,
wish
put this back. You got alpha.
2, it's 2.
y equals.
Oh, I got that right. Shalom.
Wait, okay, so.
Mashallah, bro.
Salam, Ethan.
Salam alaikum.
2.0.
Alright, those are the values you should have gotten.
Yeah. That's what I got.
I got something akin to that.
Akin to that.
Quite
So-
randomly.
Looking at our values, okay, as our x values are getting closer and closer to 0, what does it look like we're getting closer and closer to?
2.
2. So we would say that our limit equals
Does that mean you
I
can't
didn't
do
have
zero,
so
or
We
far.
just like figure, like we just.
I
I mean, like what? Like if I look at, I'm getting 1.9999.
And it's always the.
I'm getting 2.00005. That's close to 2.
Okay.
This is what I had to do for my freaking y equals 1.
4
I
zeros.
barely changed anything.
What happened?
Okay.
Threads?
Questions on that one?
What, like school shooting threads? I know. You got arrested. That's cool. Something about threats. Like telling parents to intervene before it gets out there. Yeah. If they like see or hear something about it.
Alright,
it's gonna be fine.
bring it back.
My bad.
Test came out. It's
Alright, so let's look at an example. This one, notice, you don't have to write this down. Basically what it's saying is we had to look at both the positive and the negative side. Agreed? So that's what we call a left-handed limit and a right-handed limit. It's basically approaching the x value from the left and from the right. And in order for our overall limit to like equal 2, both my left side and my right side would have to equal 2 as well. So basically all this is saying is that in order for the overall limit to exist, the left side and the right side have to be equal as well.
still good.
Which, if we have something that looks like this, it might not be.
Because it's piecewise.
It is a piecewise function. So, if I'm looking at, so in part A, it asks us to look at the limit as x goes to 2, and then it has like a little subtraction sign. That doesn't mean negative 2, that means 2 from the left. If the negative symbol comes like after and it looks like an exponent, that means from the left side. Okay? So, we're approaching 2, which is our x value, but we're following the left hand of the graph. So what y value is this left side approaching? 3. So the limit as it approaches it from the left is 3. What about the limit as x approaches it from the right? So again, we're approaching 2 still, but this time we're doing it from the right. So what is it approaching this time? 1. So then that means that our overall limit of g of x does not exist. Because notice 3 and 1 are not equal to the same thing. So I can find the left side and the right side, but if they don't equal the same thing, the overall limit doesn't exist. Which is different than on part B, because notice, what does my left-handed limit as it approaches 5 equal? 2. What does my limit as x approaches 5 from the right equal? Also 2. Okay? Which means that this time we can find the overall limit, and it equals 2. Now, so notice, yes, someone mentioned it. What is g of 5? It's like 1.15.
One-ish.
Okay? So the dot would give me my actual value. Okay? So the value at 5 is 1.5. However, again, we're kind of thinking like if I didn't know there was a dot there, where does it look like my graph should be? And it looks like it should be at 2.
Mm.
Questions on
So we're
that?
just like jumping to conclusions about the graph.
I mean, it's not jumping to conclusions because you can see the graph, and because I'm saying, what is my graph approaching? I just kind of saying, like, that's another way to kind of think about it.
What should it be? Like,
We should
What should what be?
no, like,
define our expectations.
Okay. So let's look at a few more graphs.
fun.
Well,
Oh,
sure,
I don't know how to write.
absolute value of x.
Limit.
Yeah, so what does our absolute value do?
Takes away a negative.
Takes away the negative, makes everything positive, right? So if I'm plugging in things to the left of the x-axis, right? It's still going to be positive, but I'm plugging in negative values, agreed?
Yeah.
By plugging in things to the right of the x-axis, I'm also getting positive, but I'm plugging in positive values. So notice that in order to be able to do that, we would have to look at both cases, the positive x values and the negative x values. So we would actually break it apart into two separate expressions. So we would have negative x divided by x would give us what?
X.
Negative 1. And then x divided by x would give us positive 1. And it's going to change at our x-axis. So this is what our graph looks like. So before my x-axis, it's going to be at negative 1. After my x-axis, it's at 1. But what's happening at 0? Is it approaching anything? So from the left side, what is it approaching? Negative 1. From the right side, what is it approaching? Positive 1. They, what?
Is it approaching if it's already there?
If what's already there?
Like the,
It looks like it's out.
like it is at one.
I know.
Oh no.
Yes, like if it's, because again, you, like I said, you can kind of think about it like continuing the same pattern. If I'm already at 1, right, we're approaching that same value because it's consistently staying there. Does that make sense? So it says show that the limit does not exist. Well, why would that limit using what we just talked about not exist?
Because the A from the left and the A from the right.
Not the A, but
Limit.
the L. So we would say the limit as x approaches 0 from the left is what?
Not the same.
What does it equal though? Negative 1. And notice that that does not equal 1, which is our limit from the right.
You just write it as one big one.
Yeah. Just to see. That's okay. I mean, or you could say, like, notice that the limit as x goes to 0 from the left is equal to negative 1, the limit from the right is equal to 1, and negative 1 does not equal 1. We basically just have to say that they do not equal. Okay? Now, our next one, we want to look at 1 divided by x squared. Yeah, so in your groups, I want you to decide if this limit exists, and if it does, what it's going to, or if it does not exist, why it doesn't exist.
As it approaches 0, A is 0, right?
But no, it's
Yeah.
not. Because the Y line.
This minute was A 0.
Oh no.
Yes, a is 0, so the limit as x approaches 0.
Does it have to be a set number?
That's what you're trying to decide.
So no.
Zero.
In
Zero
infinity-
next, nothing else.
Yeah, I feel like in calculus,
Zero, comma,
infinity is, I don't think infinity is a number though.
Zero, no.
It's not really a quantity. It's kind of a concept. So.
Well, wait, can I take a picture of the
Miss Bennett, are we putting infinity as a quantity or as a concept?
I don't know. What do you think?
That's so like. I'm gonna say no because that's my opinion. Let's say yes.
Like they don't like.
The amount of zeros after the one thing because it's going on. It's just gonna keep getting.
Do you hear yourself? It's like after infinity? What is after infinity?
So you can count up past infinity.
Yeah.
What is
Well,
past infinity?
It's
Anything
not-
past infinity is
I'm gonna say no because it's not a pretty one value.
no.
Alright, have we come to a decision as a table?
Yes.
So, how many of our groups feel like it does exist? No one? How many of our groups feel like it doesn't exist? Okay, why does it not exist?
It has an asymptote.
It does have an asymptote, but do they approach the same thing?
It doesn't go to one
The
value.
asymptote is like
Yeah, I know, but like what are my left and my right side approaching? Is that the same on both sides?
But it's not a limit because there is no limit.
But why?
Because infinity is limitless.
They are.
That's not what this means.
They are both.
It's for it to be a limit does not mean that it is limited necessarily.
They are both approaching one
Okay.
value, but that's
So
one
it's
value. Wait, no, wait.
They are both approaching the same
The same
thing,
thing, but it's not one value.
but it's not a value. Correct. So
Oh, so it's no?
the answer is it does not exist. However, we do need to understand why. So notice that this does equal positive infinity. Okay, and we can use limit notations to describe asymptotic behavior. Okay,
Ooh.
asymptotes behavior.
No, I got that.
Because basically we're saying that both sides are approaching infinity. However, the overall limit does not exist because I said that my limit has to approach L, and L has to be a value or a number, and is infinity a specific value?
no.
No, it's a number that gets bigger and bigger and bigger and bigger. Does that kind of make sense?
Mm.
Now, to go off of what you were saying, it doesn't necessarily have to be limited as far as like, does that make sense? Like, it can go on forever. So,
Ooh.
let me see if I can find. So let me see if I can pull a chart of this. Alright, so here's one. So notice that as my function goes on, right? So like as x is going towards infinity, what's happening to our y values? They're going up and down, but what are they getting closer and closer and closer to? Zero. So just because something goes on for infinity doesn't necessarily mean that it doesn't approach something. So like in this case, my y values would be going towards 0. Okay? Alright, now let's look at one last one. And this one's my favorite one.
I can see why.
Oh, God.
Alright, so we have the limit as x goes to 0 of the natural log. 1 divided by x minus sine of x divided by 1 minus cosine squared of x. Okay? So, what might that graph look like?
Is that 1?
Yeah,
1 minus x?
So, the natural log of 1 minus x minus sine of x. Oops. all divided by 1 minus cosine squared of x.
It's not percent of